Okay, so today's topic is concerned with measurements in chemistry, and so um, we'll talk briefly about the metric system, or what I prefer to call the international system of units. We'll distinguish between exact and inexact numbers. We'll talk briefly about how uncertainty in measurements is indicated through the use of significant figures, and we'll talk about how we deal with significant figures within mathematical operations, and finally we'll explain how to convert between scientific notation and decimal notation. So this topic has a lot of mathematics in it. It's important that we take it slowly and just keep working at it. Don't allow yourself to become overwhelmed, but give yourself plenty of time to learn the material, and most importantly, practice a significant number of problems. Okay, so all measurements have at least two parts, namely a number, or sometimes called the magnitude, and the units associated with that. Measurements may also include other things such as the direction, i.e. I drove at 30 miles per hour east, west, north, south, whatever. And sometimes they have an estimate of the variability in the measurement. So multiple measurements are taken and the variability in that measurement is expressed in some way. An example would be today's maximum temperature was 27.5, which is the magnitude, plus or minus 0.2, which is the variance, and then we've got degrees Celsius being the units. So in chemistry we use a modern version of the metric system, which is referred to as the international system of units. Now this was originated in France, so in French we call this the Système International, and so we'll often refer to SI units. Unfortunately, the metric system is not widely used in everyday life in the USA, and so as a consequence you must become efficient at using conversion factors and formulas to transform measurements between different systems of units. So there are a couple of examples where some fairly serious incidents have resulted from errors in converting between systems of units. So one example here is the Gimli glider, which there was a confusion between pounds of fuel and kilograms of fuel, which was very unfortunate because a kilogram is more than twice the volume of a pound, and so this plane ended up running out of fuel and had to glide into the former Air Force base at Gimli, which had been converted into a raceway. Fortunately, no one died. This is a kind of an embarrassing one. The Mars Climate Orbiter was lost in space because of an conversion error between different systems of units. So some of the common SI units that we'll use in chemistry are shown below. There are 7 base units in the SI system. We won't use all of them in this class. Some of them deal with things like luminosity and other measurements that we're not particularly interested in. So mass, commonly measured in grams in the lab, and that has the symbol lowercase g. Volume, the base unit is litres, although in the lab we'll often use something a little bit smaller, and the abbreviation for the litre is an uppercase L. Distance, the base unit is the metre, and that has abbreviation lowercase m. And for time, we use the unit seconds, and that has the abbreviation lowercase s. So in chemistry we're often dealing with very large numbers or very, very small numbers, and to help with that, a system of prefixes that can be placed before units is often used or has been developed. So these prefixes serve to multiply the unit that is followed. So the prefix mega, which has the abbreviation uppercase M, means multiply what follows by a million. Kilo, which has the abbreviation lowercase k, means multiply what follows by 1,000. Deci, which has the symbol or the abbreviation lowercase d, means divide by 1/10 or divide by 10. Centi, which has the abbreviation lowercase c, means divide by 100. And milli, which has the symbol lowercase m, means divide by 1000. And micro has the Greek letter for its symbol mu, which means divide by 1 million. So take a note here, particularly mega and milli. The distinction between the abbreviations here is simply a difference between uppercase m and lowercase m, but the multipliers differ by a factor of 1 billion. So if one was to confuse mega with milli, say perhaps in the dispensing of a medication, then you could be giving somebody 1 billion times more of that medication than what they were needing, and that would probably cause them a problem. So I would like you to memorize these 6 prefixes here. There's a more extensive table in your book that you can use when you're uncertain, if you encounter a prefix that you don't know what it is. But these 6 here I'm expecting you to know for your tests and your quizzes and midterms, etc. Okay, so now we move on to a discussion between the distinction between exact numbers and inexact numbers. So exact numbers are numbers that have no uncertainty associated with them. That is, we are certain what they are. And examples would be whole numbers of objects. Because, for example, we are completely certain that there are 3 pennies in this photo. And another example of exact numbers are unit definitions. For example, it is defined and there is no uncertainty that there were 12 inches in a foot, or that there are 8 1/8 of an inch in an inch, or 10 millimeters in 1 centimeter. All of those things are defined and there is no uncertainty about those numbers. Inexact numbers are numbers that have some uncertainty associated with them, e.g. the measurements, and these uncertainties arise due to limitations of the observer and limitations of the device being used. For example, this is a drawing of a ruler that is divided, the gradations are every 100 centimeters, and at this mark here, it looks to me that this is 300, but there's a little bit of uncertainty about it. It's about 300 centimeters. Looks like it's a little bit higher than 300 centimeters, but there's some uncertainty about that measurement due to the limitation of the scale. If there were more marks on this ruler, then I could be more certain about this measurement. So in chemistry, whenever we make a measurement, we include one estimated digit. So in this case, to record this measurement correctly, I would have to include one digit that lies in the tens place, because the smallest increment on my scale is in the hundreds place. So I will record the above measurement as 310 centimeters. Now the important thing is to note is that the digit that's in the tens place is uncertain. Some people would say, no, it's not 310, it's clearly just 300. But it's going to depend upon the skill of the observer. This one here, there is some uncertainty about that digit there. The last digit in any measurement will vary depending on who has recorded it and will contain some uncertainty. So for example, here we have a student who's doing a great job of reading off the volume of a measuring cylinder. They're holding their eye level with the bottom of the meniscus, so they're avoiding parallax error, and they're reading accurately just the value on the scale, just where the meniscus touches. Now this scale, its smallest increment is in the ones, so when we record a measurement from this measuring cylinder, we'll include one estimated digit that is in the 0.1 in the tenths position. So this measurement, because the student is judging that the meniscus sits exactly on the mark at 32, we record a 0 in the tenths position. So unlike in your math class where you're told, oh, if there's a 0 after the decimal point, it doesn't count, the 0 doesn't alter that the value is 32, but the 0 indicates to us that the smallest increment on our scale was in the ones column, and that this is the first estimated digit. So it's important to include this 0 in this case because it's telling us about the quality of our measurement, and so we need to leave it in. So we can define the number of significant figures in a measurement as the number of digits we known with certainty plus 1 that is estimated. Okay? The number of significant figures that we know, the number of digits that we know with certainty plus 1 that we have estimated. And that's the number of significant figures. So when we look at a measurement and we want to know the number of significant figures in that measurement, we need some rules to guide us, and the first rule is that all non-zero numbers are significant. For example, 15, both the 1 and the 5 are non-zero, has 2 significant figures. When the number contains 0, it gets much more complicated. So zeros can be in 3 places. They could be at the front of the number, and I call those leading zeros, and they are never significant. So if we look at these two numbers, the zeros out the front here are leading, and they are not significant. The 1 and the 2 are non-zero, so they are both significant. In this number here, the leading zeros are not significant. The 1 and the 2 are significant, so both of these numbers have 2 significant figures. Confined zeros are zeros that lie between non-zero numbers. I also refer to these as buried zeros sometimes, and they are always significant. So the leading zeros in this number here are not significant, but the 4 digits 5, 0, 0, 3 are significant, the 2 non-zero digits and the 2 buried zeros. So this number has 4 significant figures. If a number contains a decimal point, trailing zeros or zeros that appear at the end of a number are significant. So this number has 1, 2, 3, 4 significant figures. But if a number does not contain a decimal point, then trailing zeros are not significant. So in this case, the trailing zeros at the end of this number are not significant, only the non-zero numbers 2 and 5 are significant. So summarizing, all non-zero numbers are significant. Confined, or what I sometimes refer to as buried zeros, are significant. Leading zeros, zeros that appear at the front of the number, are not significant. And trailing zeros, zeros that appear at the end of the number, are only significant if the number contains a decimal point. So frequently in chemistry we combine several measurements. We did this in the lab when we were calculating the density of our egg. We measured the mass and we measured the volume of our solution. So the question is, if those two measurements have different numbers of significant figures, how do we express our final answer to the correct number of significant figures? So there are some operational rules that allow us to resolve this issue. So when we divide and multiply measurements, our answer contains the number of significant figures in the number with the least number of significant figures. So for example, in calculating the density of an object, I measured its mass to be 26.003 grams and its volume to be 25.0 milliliters. So 26.003 has 5 significant figures, 3 non-zero numbers and 2 confined zeros, whereas 25, the measure of volume, has 3 significant figures, 2 non-zero digits and a trailing zero that appears after a decimal point. So my answer should have 3 significant figures. For addition and subtraction, we use the number of digits that appear after the decimal point as our basis of determining how many significant figures should appear in our answer. And our rule states that the number that contains the least number of digits after the decimal point, that is the number of digits that we will have after the decimal point in our answer. So if I was measuring the total mass of an object in a container, and I measured the container separately, and then I measured the mass of the object separately and added them to those two numbers together to get the total mass. If I was doing that exercise, which seems a little bit pointless. Why not just put the object in the container and measure it all at once? Then I would add the mass of the container to the mass of the object. The mass of the container here, it has 1, 2, 3, 4 significant figures, but 1 digit that appears after the decimal point. And the mass of the object has 1, 2, 3 significant digits and 2 digits that appear after the decimal point. So my answer must contain 1 digit after the decimal point, because the mass of the container has only 1 digit after the decimal point. So my answer would be 209.2 with 1 digit after the decimal point. Grams. Our measurement needs units. Okay. So when I entered the numbers that I used to calculate the density in the previous example into my calculator, I obtained quite a long number. This number has 1, 2, 3, 4, 5, 6 digits, but I said that my answer should contain 3 significant figures. So what do I do with all of these other digits here? Well, what I need to do is I need to round off in some way to include the information that's contained in these 3 digits. So what do I do with these numbers? Well, I have to round off. And our rounding rules that we will use in chemistry are: if the first number being dropped is less than or equal to 4, leave the last significant figure alone. Don't change it. If the first number being dropped is greater than or equal to 5, increase the value of the last significant figure by 1. So in this case, when I do this calculation here, this is my result. I know I need to round off to 3 significant figures, so I will simply eliminate these 3 digits and leave my final significant figure, the digit in the third place here, alone, because 0 is less than 4. People often ask, what role do exact numbers play in determining the number of significant figures in calculations? Exact numbers play no role. We behave as though they do not affect the number of significant figures at all. So if I had cut 3 sticks and I had measured each of those sticks to have a length of 30 centimeters, I could calculate what the length of those would be if they were placed end to end by doing 3 times 30 centimeters. Now there is no uncertainty in the fact that there are 3 of my sticks, so this is an exact number. So therefore I express my answer to 1, 2, 3 significant figures. The trailing zeros in this case count as significant figures because there is a decimal point in my number. So in chemistry, we mentioned before that we often use very large or very small numbers, and so using a decimal expression of these numbers can cause problems. We can make mistakes and it's just hard to read them. So recording this number to the correct number with the correct number of zeros, you can see that it's likely to be problematic. And similarly with very small numbers, an error is likely when we express these numbers in decimal notation like this. And very large and very small numbers are common in chemistry. So we can express very big numbers and very small numbers in scientific notation. So here is the number 110,000 in decimal notation, and here it is expressed in scientific notation. And you can see there's much likely to be an error when we write it in this way. So our decimal notation includes a coefficient, which is always a whole number with 1 digit to the left of the decimal point. And it includes an exponent, which is a power that we are raising 10 to. And the final term here, the power of 10, we refer to that as the exponential term. Okay, so how do we convert a number from decimal notation to scientific notation? So to convert between scientific notation and decimal notation, the decimal point is moved to the position to the right of the first non-zero number. So here I have the number 5015, and to move the decimal point to the right of the first non-zero number, I would need to go 1, 2, 3 spaces to the left. If the decimal was moved to the left, the exponent will be a positive number equal to the number of spaces the decimal was moved. So in this case, the exponent will be 3 because I moved the decimal point 1, 2, 3 spaces to the left. And then here we have our coefficient with the decimal point 1 space with just 1 digit to the left of it. If in moving the decimal point so that there is just one whole number, non-zero number, to the left of it, I move to the right, then the exponent will be a negative number, equal to the number of spaces the decimal point was moved. So here I have the number 0.0034, and I need to move the decimal place 1, 2, 3 spaces to the right. Okay, and so then my coefficient will be 3.4, and because I moved the decimal point to the right, my exponent will be a negative number, and I moved it 3 spaces, so that becomes -3. In scientific notation, only significant figures are included in the coefficient. So here we have this number here, it has 2 significant figures. So I move the decimal place 1, 2, 3 spaces to the right. Okay, and now I have one non-zero number to the left of the decimal. So my coefficient will be 3.4 and my exponent will be -3. In this case, I have a number 510,000, and I have 1, 2, 3, 4 trailing zeros that are not significant. This number has 2 significant figures. I move my decimal point 1, 2, 3, 4, 5 spaces to the left, so that I have only one non-zero digit to the left of the decimal point. So in this case, my coefficient becomes 5.1, and because I moved my decimal point 5 spaces to the left, my exponent is 5. Okay, so that concludes today's lecture. Thank you.